All right, so this week we'll finish up chapter 5. The last thing we have to finish in section 5.4, part 2 is going to deal a little bit with solving equations that we used to have to do on the calculator with an intersect. But now we're going to learn how to solve it with algebra. We'll review a few properties of exponents, and then we'll finish up with what's called a power regression, and how to do it by hand, and then also on the calculator. All right, so the first one, I want to just practice rewriting that expression in terms of a to the x, a to the y, and a to the z. Okay, so what we got to do is look at that exponent and figure out, okay, what would cause you to have to add two things together to get a result in an exponent? And then after, we'll look at what would cause you to multiply together two things to get an answer in the exponent. All right, let's start with addition. Does anybody remember the rule for when you add exponents? What's the calculation? You can even give me an example or just describe it in words for when you have to add what's in the exponents together. Yeah?
When you multiply two, like, if it's so, say it's like 2 to the x times 3 to the y. Or does it have to be the same variable?
It doesn't have to be the same variable, but it has to be...
Oh, the same base.
It has to be the same base. So that would give you 2 to the x plus 1. All right, so let's do that idea with the first part. We have a to the 2x, so it's basically like what I just did, plus 3y. So if I want to kind of start to separate this out, it would have been a to the 2x. And what would be next to that? So I would do plus 3y in the exponent. Scott?
It would be a to the 3y.
Yeah, times a to the 3y. Now the last part there says minus z. Does anyone remember the rule when you would subtract to get an answer in the exponent? Yep. When you have division. So if you're subtracting z, then you must have been dividing by a to the z. Okay, so that's the first part. So now we've got a to the z. That's good. But we don't want the 2 next to the x, and we don't want the 3 next to the y. Does anyone remember the property, or what would have to happen for you to multiply two things together to get an answer in an exponent? Anybody remember where you use that property? Where you multiply two things together to get the answer in the exponent. Yeah?
It would be like a minus 2 times I.
So go ahead. Can you give me an example, or just say what you said again?
A to the 2 to the x.
Yeah, a to the 2 to the x. When you have a power to a power, you multiply. I'm just going to switch the 2 and the x, which is exactly the same thing, because they want the x on the a. Okay? So a to the x squared. You've now rewritten that in terms of a to the x, and you're doing something to it, times a to the y, and we're going to do something to that. So basically, we've rewritten it the way they wanted. Okay? Just using our rules for exponents. Any question on that? Okay, so that might come in handy depending on your problem to help you simplify something. But in this case, that's all you have to do. So that's it. All right, now we're going to look at solving an exponential growth or decay. It doesn't matter which one. Same approach, algebraically. So if you look back in your notes, we've done this problem. Okay, it's a problem from the section where we did exponential growth. You've got a population of 50,000 people going up at 2.5% every year. They want to know how long before the population hits 100,000 people. And I think when we did it, it was like 27.07 or 28.07 years, something like that. Okay, but you could look back at your notes and you'll see that. But what I'm going to do differently is, well, we'll review how we would have solved it, okay, and the same type of thing you would have done on the test. But then I'm going to show you an algebraic way to solve it. Now, before we can solve it, right now I don't have anything to solve. So what do I have to do first? Yeah, Nick?
Create an equation.
Yeah, I got to create an equation, specifically one for exponential growth, because we have something increasing, and whenever something increases by the same percentage, every day, every month, every year, that's exponential growth. All right, so let's start with our population as a function of time. So what do you start with in the exponential growth formula? Does anyone remember? First thing you write down? Yeah?
Initial population.
Yeah, the initial, whatever it is, in this case, a population. So 50,000 times, and then in parentheses, does anybody remember what goes in the parentheses for exponential growth? You don't have to plug in what we have yet, just the general expression. Abby?
It's 1 plus the rate.
It's 1 plus the rate. Anything you got to do with the rate?
We should turn it into decimal.
Yes. So it would be 1 plus 0.025. You can either write it like that or just simplify it right now. And then the last thing is to the t. Any question on that? Now we want to know when we're going to hit 100,000. So where would 100,000 get plugged in there? For P of t or t? Yeah?
P of t.
P of t. That's the population. So you plug that in, and you'd have 100,000 equals 50,000 times 1.025 to the t. Now, how would we have solved that using the calculator last week? What would we have done at this point, which I'm not going to do right now?
Graph both sides of the equation.
Yeah, graph what's on the left in y1, graph what's on the right in y2, okay?
And then find the expected.
Yeah, and equals visually means where they cross, and that would be the answer for t. Okay, well now we're going to solve it algebraically. So anybody see something I could do to both sides to start to get the t by itself? I can at least get something away from it. Yeah? Yeah, we can start by dividing by 50,000. So I get 2 equals 1.025 to the t. All right, now the problem is, well, what's the problem with that equation? Why couldn't I give that to someone in Algebra 1 and have them solve it, most likely? What's in there that kind of complicates it a little bit? Yeah?
It's exponents instead of just regular variables.
Okay.
Variable as an exponent.
Yes, the variable is an exponent, and anytime we have variables as exponents, we have to use log somehow. So there's a couple ways you can solve it if you know the change of base formula. We could do that. If we don't, I'm going to show you another trick that would lead into that. So I'm going to take the log of each side. As long as I do it on the left and the right, it's still balanced. And the reason I'm doing this is because now we have a rule where if you have an argument that has an exponent in a log, you're allowed to move that exponent somewhere. Does anybody remember where you can move the exponent?
In front of the log.
You can put it in front, and now we've solved the problem of having an exponent that's a variable. So we have log of 2 equals t times the log of 1.025, and now my last step would be to get t by itself. So how would I get t by itself? Scott?
Would you divide log 1.025 by log of 2?
Divide log of 1.025 by log of 2. Not quite. You said this, right?
Oh, other way.
Yeah, other way around. Divide each side by log 1.025. And log 1.025. That's gone. And there's t. Now, since there's no base on this, it's whatever base I picked at this step right here when I took the log of each side. What base was I assuming? Yeah,
10.
I was assuming 10. So now, let's type that in. And round it off and see what we get. And I think when we did it graphically, it's about 27.07 or something like that. So log of 2 divided by log 1.025. 28.07 years. Okay, and I'm going to show you something a little different. I'm going to take the ln of 2 and divide by the ln of 1.025. And I get exactly the same thing. It actually doesn't matter which one you use. Okay, any question on that? So let's go back to what we had, because there's actually a faster way to do this using what's called the change of base formula. 2 equals log 1.025 to the t. Let's change that into log form, which is what I was starting to do, but I want to write it out. What's the base in 2 equals 1.025 to the t? What number is the base there? Devin?
1.025.
That's going to be the base on my log as well. And now, yes, last week I said logarithms always equal what kind of number? Yep.
Exponents.
Logarithms always equal exponents. And now the only thing left is the 2. And where would that get? Well, I know where it's going to get plugged in, but does anybody remember what that's called? The thing you're taking the log of?
The argument.
The argument. So here's a formula to find t. Well, here's another formula to find t. Okay. Log 2 divided by log of 1.025. Two different expressions that give you t, so that means they're the same thing. So what I'm trying to show you here is how you can take the log of something that's a base other than 10. Right? And that's the change of base formula. So in general, if you had log base x of y, and x wasn't a 10 and it wasn't e, you don't have a button to type it in directly. But you can rewrite it in a way that you can type in. Log of the argument divided by log of the base. So log of the argument divided by log of the base. And I kind of showed you this in the last one. It doesn't really matter whether you use regular log or you use ln. I would just pick one way and I wouldn't bother worrying about the other way. Either do it the way on the left or the way on the right. Now what we did here isn't really a proof. All I did was show you something numerical that suggests that's the pattern. Okay? But it turns out that it is. So can somebody tell me how you would type in that on the calculator. So I don't have a button for base 6. So how can I rewrite it so I can type it? Yep.
Log base 13 over, no, sorry, log 13 base 10 over
Base 10,
log,
yep.
base 10 6.
Yep. So it's the common log of 13 divided by the common log of 6. Okay. Or you could do natural log of 13 divided by natural log of 6. Same thing. Okay. So any questions on that? So if it seemed confusing, you don't have to use the change of base formula. But I would rather use the change of base formula at this step than to go through all this other stuff. Take the log of each side, then move the exponent in front. That's kind of a lot of extra steps to me. But either way, as long as you get 28.07. Any questions on that? I think in section 5.5 is where they show this formula, but it kind of makes sense right now since we could use it on the problem we just did to show it to you. All right, so the last thing we're going to look at is what we call a regression. Okay, there's different kinds of regressions. There's linear regressions, which is something you might have done in Algebra 1. You've got a set of data, and you try to find a line that fits the data. If you just sketch the line by hand, that's called a line of fit. If you actually use a formula, you can calculate what's called a line of best fit, meaning you give me like 15 data points. I'll do some special calculations, and I will find the best possible slope and the best possible y-intercept that goes through all those points. The best that it can. Well, sometimes you have a set of data that wouldn't be modeled well with a line. Looking at that set of data, does that look like a line would be a good model for it? No. I mean, if I was going to put a line, maybe I would guess something like that. Kind of goes through the points. But it's really only accurate here and here. Everywhere else, assuming the pattern continues, my points are going to continue that way, and my line's going to continue that way. The error is pretty bad. So, instead of finding a line of fit, or a line of best fit, we could find a curve that fits the data. So our goal is going to be to figure out the equation of that curve. Sometimes it could be an exponential curve. In the case we're going to do, it's going to be a polynomial curve. So strictly, it's not going to be an exponential equation. We're going to find a polynomial. Like maybe that's a parabola where x is greater than 0, or maybe it's part of a cubic. If you think of the other side coming down like that, maybe it's the right half of a cubic, but we'll figure out what it is. Okay. So we're going to be finding what's called a power model, or a power function. And when we're done, a and m both have to be numbers. So we solve for a, solve for m. And just to show you, well actually I'll show you the calculator after. We'll do it by hand first, and then we'll do it on the calculator. Okay, so before you use a power function, first you have to decide, is that even the right thing to do? Okay, if you're given a set of points, should you start the process of finding a power model for your data? Okay, and then if the answer is yes, I'll show you how to do it. So first I'm going to try to point out to you how you can figure out whether or not a power model is the right thing to do. I'm going to take that equation and I'm going to do something we did before. I'm going to take the log of each side. Specifically, I'm going to do natural log It doesn't have to be, but that's to follow what the book does, that's what I'm going to do. So I took the natural log of each side. And now, inside the argument on the right, what operation am I doing with the a and the x to the m? Tell me what are we doing there with the a and the x to the m? Yeah. Yeah, you're just multiplying them. Does anyone remember the rule when you multiply inside a log, how it could split into two? Yeah.
In this case, it would be log of a plus the log of x to the m.
Yes, so it would be log of a plus log x to the m. When we say log, we mean natural log.
Yeah.
And then one more thing I can do, I think we already looked at this today, with that exponent of m, we can put it in front. So what I've done is I rewrote it, the order a little bit, because I want you to hopefully see something. But you have mlnx plus lna. Does anybody see what that kind of looks like? If you cross out something, it almost looks exactly like this, yeah? Yeah, it looks like the formula to find m, like the slope.
Yeah. Well, y plus b.
Right, the point slope, yeah. If you cross out, don't do this, because I want you to keep what you have in your notes. But if you cross out the ln, you have y equals mx plus b, or y equals mx plus a. It's basically the same thing. So the fact that it kind of looks like the equation for a line, if you cross that out, is important. And because of that, and the fact that we have the ln everywhere, I can say the following. We can say that ln of y is the linear function of ln of x, where our slope is m, and the y-intercept is ln a. So I can't say that y is the linear function of x, because it's not. But I can say the natural log of y is the linear function of the natural log of x. And that's a hint at how you can figure out whether or not to use a power model. So what that basically means is if you have a table of data, a bunch of x and y values, okay, you get a whole table of x and y values. If you take that whole table and take the natural log of every number in the table, so now instead of x, you have the ln of x, ln of y. You take the ln of every number in the table. If you do that, and this table comes out linear, then that's how you know you should be using a power model. So you take your table of data, you take the log of every number in the table, and if that new table looks like it's a straight line, power model is the way to go. How can you tell if the table is a straight line? Graph it. Graph the points in the table and see if they look straight. All right. So I already told you the first step. How to decide if you should use a power model. Create an lnx, lny table. Do that by taking the natural log of every number in the table. Graph it. See if the points look linear. If they do, then continue on to step 2. Now, after you create that lnx, lny table to see if your points are linear, you're done with it. You never use it again for the problem. The only purpose of it is to determine if we should use a power model. After that, you can throw the table away. You don't need it. So everything else here, assuming we're going back to the original table of data, XY table. Right, so there's a couple things you have to find. Okay. You have to find B, or actually, what did I call it? I called it A. So let me fix that. So let me put this up at the same time. So find A. Next step, find M. Now, after you find A and M, that's pretty much your answer. Your final answer should look just like that. Find A and find M. M is kind of like your slope. A is the y-intercept. If you were to draw this table up, the ln x, ln y table. And then after you find A and M, we're going to write our final answer. If you put A or B, it doesn't really matter. I just put B because we're used to thinking y equals mx plus b. I think your book uses A. Either way. Okay, so let's go through a problem and see how we would calculate a power model for this data. Okay, does everybody have the steps? All right. Okay, so there's our table of data. First thing I want to do is figure out, should I try a power model? What do I have to do to every number here to figure out if I should be using a power model? What am I going to create? Yep.
Find a log.
Yeah, I'm going to create a log table of all these values. Okay, so let's create an ln x, ln y table. Okay, and this table has one purpose, to determine if you should use a power model. And that's it. Okay, what I can do to actually speed up, so I don't have to press ln 8 different times, is, and this is also going to help us for the next step, put all these points in the calculator. Stat, edit, put your x's in L1, put your y's in L2. So 1, 3, 5, 8, 5, 31.2, 73.1, 160. Now, what I can do is I can go back to the main screen, press ln, and now I'm going to take the ln of L1. So it's going to take the ln of every number in L1 at the same time. So ln, L1 is second 1. And there's all the values. So I get 0, 1.1, 1.6, and other one, you just got to scroll over to it, 2.1. It just saves you from pressing ln each time. If you want to do them one at a time, you can. Now ln of L2, 1.6, 3.4, 4.3, and 5.1. And now, what am I going to check about this table? What am I checking to see? Yep. I'm checking to see that it's linear. Exactly. Okay, I'm going to check to see that this table is linear. Okay. So let me graph those points and see what we're looking at. Okay, and of course it's decimals, so do the best you can. 0, 1.6, 1.1, 3.4, 1.6, 4.3, and 2.1, 5.1. Maybe about right there. Okay, let me draw a line and see, do those points look like they're pretty close to the line? Yeah.
I just have a question. How did you put the numbers and how did you put them into the calculator?
Stat, edit. So, all right, so we've decided, okay, it looks like these are aligned. We're good. So that's definitely what we're going to use. A power model is what we're going to use. Now, there's actually a couple ways you could do it from here. Basically, if you can find a line of fit, a line of fit for that data, or you can find a curve of fit for the original data, it's going to be the same answer. Right? Obviously, if I find a line of fit for the ln table, my numbers are rounded, so it's not going to come out exact. But basically, if I go back for a second, the slope of this line right here, which actually looks pretty good, the slope of that line is going to be the exponent. The y-intercept of that line. So basically this point right there, the y-intercept of that line is going to be that number. Okay? That's basically what we're looking for. Okay. Any questions about why we're going to use a power model? Okay, so let's go back to I'm going to use the original data because it's not rounded, it's more accurate. And plus, that's the point. We're going to always go back to the original table. So let's take our equation, which is right there, and we're going to fill into it. The first thing I want to solve for is A. In that original table, did anybody see a coordinate that would be pretty nice to plug in? There's a coordinate there. I'm going to be plugging it into what's in that box. And that box is going to have me take the ln of stuff. And if you look, there's something nice that happens with one of those coordinates. Yeah? Yeah. How come? Yeah. Basically, this is, and you'll see this probably in a second, but plugging in that point is kind of like if I said to you, here's 2 points. I want you to find the equation of the line that goes through them. Okay. Well, and I want you to start by finding your y-intercept. Well, if you're using this equation and you plug that point in, you basically have your y-intercept right away. Right? Y equals mx plus b. Y-intercept is 3. Exactly the same thing is going to happen right here. Same idea. So let's scroll down. And we're going to be filling into ln of y equals m ln of x plus ln of a. All right, so ln of y equals m ln of x, here's my x, plus ln of a. Hey, ln of 1, we just did that in the ln table. We already know the ln of 1 is 0. 0 times m That's gone. So, based on that equation, what's A? Yeah.
Ln of 5 or 6.
So what number would you plug in on the right to make it equal to what's on the left?
5.
What's your final guess?
5.
5, yes. So A is 5. So what you just found, if you're thinking about it in terms of your power model, where's my equation? Right here is the coefficient of x. You just found the coefficient of x. If you're thinking about it in terms of a line, the ln of 5 is the y-intercept of this line right here. And exactly as it should be. ln of 5 is 1.6. That's my y-intercept. Okay. All right, so we've got A. We already determined if we should use a power model. Now we're going to find M. Okay, to find M, pick another point in the table. What do you think a good point to use because the numbers aren't as messy? Let's see another good coordinate. Yeah? I would use the 8,160 just because you don't have any decimals. Okay? So let's plug that in. Okay, so this will solve A. And now we'll solve for M. So ln of y equals m ln of x plus ln of a. So ln of 160 equals m ln, what was the point with 160? Was it 8,160? Plus ln of a, I already know a is 5. My advice is don't write 1.6, just leave it like that because nice things are going to happen. The goal is to get everything combined into one ln on the right. Because if you can have ln of stuff equals ln of other stuff, you can basically cancel the ln's. And then you're just left with a simple algebra equation, maybe combine like terms, and that's it. So, can someone tell me the first step on the right-hand side to recombining that into a single ln? What could I do first? Yeah?
Make m the exponent.
Yeah, exactly. Make m the exponent. All right. And now we have two logs separated with addition. So how would those logs be recombined into one? Yeah?
Multiply them.
Yeah, you would multiply the arguments. And you could write 8 to the m times 5. I just think it looks neater if you write in that order. 5 times 8 to the m. And now we've got a single log on each side. So just like we did on this problem, where we took the log of each side to get to that step, we can reverse it and go back. So get rid of the log on each side, as long as it's the same log. Cross that out. Log, that's gone. And now we're basically left with an equation to solve for m that's just like the population problem. If you had to, you could graph what's on the left in y1 and the right on y2. But this one I think is going to work out easier. Anyone see something I could do to get 8 to the m by itself? Yeah, Chantal?
Divided by 5.
Listen, sorry. Divide by 5. So now we've got 160 divided by 5, which that comes out nice. Anybody know what 160 divided by 5 is? Yep.
32.
32, yep. And this actually works out very nice because both 32 and 8 are powers of what number? Yep.
2.
They're both powers of 2, so if I can write them with the same base, then I can solve this very easily by hand. 2 to the 5th is 32. 2 to the what is 8? Yeah. 2 to the 3rd. And now this is why I went over the properties of exponents. You have a power to a power. So what do you do with the 3 and the m? Nick?
Power to power you multiply.
You multiply. So 2 to the 3m. And now your bases match. So now make your exponents match. What number could you plug in for m, multiply by 3, and the answer comes out to 5? Three times 1 is 5. And it's going to be a fraction. It won't be a integer. Yeah? 5/3. Yeah. 5 divided by 3 times 3 is 5. So there is your m. And again, there's two ways to think about m. Either think about m as the slope of that line, or you think of it as the power in your power model. So if that's the slope, my line should roughly go up 5 and right 3. Let's graph a line that goes up 5 and right 3 and see if it looks kind of like what I did. Up 5, right 3. We connect those two. Probably about like that. Not bad. So the line that I estimated is pretty close to what the slope really should be. So, final answer, y equals ax to the m. Y equals ax to the m. There's a power model for the data. Okay, so now what I'm going to do is I'm going to check that power model. Go to my calculator. First thing I would do is type in all the data from the original table. It's already there. Next, I'm going to type in 5x to the 5/3. But now I'm going to think about my window. Look at your table. What would be a good x min in that table? Be a good value for x min based on those numbers. Yeah?
0.
Yeah, I would go with 0. X max, you could leave at 10, that's fine. How about y min? I don't think we need negative 10. What would be a good y min? Oh, Tyler? What's my smallest y value in that table?
5.
5. So let's go a little lower than 5. Nice simple number.
2.
2? Yeah, you can do 2. I would have done 0. Doesn't matter. Okay, something you can see is fine. And then y max. What would be a good number for y max? Yeah. Yeah, 180. I just wouldn't do it right on the edge of, don't do 160, then your point's going to be on the edge of the screen. All right, let's hit graph. And right now, you're only going to see the line because I didn't turn on the points. So to turn on the points, go to y equals, go to plot 1, and hit enter. What that's going to do, if I go second, y equals, you can see a little more detail about plot 1. Plot 1 is going to graph the x's. It's going to grab those from L1. It's going to grab the y's from L2. And that's exactly how I typed them in. If you used, let's say, L3 and L4, or different lists, here is where you would change it to whatever you used. But if everybody did what I did, L1 and L2, you shouldn't have to make any changes. Okay, graph. There's your points. And does it look like the power model goes right through those points? Yeah, it's a perfect model for the data. So the more linear that the LN table looks, the better your power model is going to fit the original data. So any question on that? All right, so now we know how to do it by hand. Last thing I'm going to show you is how the calculator can figure it out for you. The only problem with the calculator is it's probably not going to get those two numbers. It's going to get close. It might get like 5.00001, and 5/3 it's going to write as a decimal, so it might get like 1.6667 or something. It's not going to get exactly those numbers. Right. The way we do it on the calculator. Okay, I don't have all the steps written, but I'm going to say them slowly, so you can either go back and watch the video or write them down. Step 1 is to type in your data. We already did that. Step 1, type in your data. Okay, after you type in your data, the next step is to go to Stat, Calc. And under Calc, there's all kinds of regressions. A regression is the process of fitting an equation to data. You could do a linear regression, that's option 4. You could fit a parabola to data, or a cubic or a quartic. You can do all kinds of regressions. We're doing a power model. So we're going to go down to power regression. So we are telling the calculator we want it to try to find a power regression model for the data. So you go to Stat, Calc. On my calculator, it's option A. Hit Enter. If you already put your x's in L1 and your y's in L2, you press Calculate. If you've made a change to that, if you put them in like L4 and L5 or some different list, you need to tell it where you put them. Now, up here it says Store Regression Equation. I'm going to come back to that, but basically what that means is whatever answer we're about to get, the calculator is going to store the entire equation in that variable. As far as I know of, that's the only variable on a calculator that can store an entire equation. Not just the slope, not just the y-intercept, like the whole equation in one variable. Okay. And I'll come back to it. Okay. So now just press Calculate. So it got 4.999993 for A, which is the number in front. Okay. They might call it different letters. I can't control the letters they use, but just look at the position in the formula. Now the B is the exponent, 1.666666727. So if you were to divide out 5/3, that's 1 2/3, 1.6 repeating. Okay, so it got the same thing we got. So any questions on how I calculated a power model using the calculator? Now, let's say you wanted to graph this. That entire thing that you see on the screen right now is stored, not sure if it's capitals or what, but it's stored right there. It's stored in that variable called regression equation. If you create a new regression, it's going to wipe out whatever's in there right now. Okay, but if you turn your calculator off and turn it back on, it should stay till you do another regression. So, if you want to graph it without actually typing in all those numbers and see what it looks like, it's a variable. So you're going to go to where it says vars. And we calculated a statistical variable. Regression is a statistical type of thing. So it's under statistical variables, option 5, and we're looking for the equation. We're not looking to do tests or other things. We're looking for the regression equation. It's right there. Reg EQ. So if I hit enter, it automatically copy and pasted. If I scroll over, you'll see the rest of it. That equation into Y1. And the point why you might want to do that is you just type it in, hit graph, and then you can check your regression and see how close it is. And obviously it's basically the same equation we just typed in. Much, much nicer to write it as 5x to the 5/3. That's the exact answer. So any question on that? Now, how close of a fit does that look? I mean, does it look like that curve is, it's okay, it's pretty good, it's almost exact? What do you think? How close of a fit is that curve to those points? Well, Tanner, what do you think?
Close.
Pretty close. Yeah, I'd say it's almost exact. It looks like it goes right through every point. Well, there's a measure on the calculator that tells you how exact is it. And it's a measure between 0 and 1. 1 meaning you've got a really, really good fit. 0 meaning it's terrible. It's the worst possible fit you could ever have. And if you go to the catalog, what's it under? There's a lot of things in the catalog. All right, so thanks to Google, now we know it's under D. You turn on what's called the Diagnostic. So if you press alpha D, it'll get you down to the D's quicker. Or you could just scroll. And go to Diagnostic on, and just hit enter. That'll stay on until you reset the memory in your calculator. Now, if you calculate the same regression again, okay, power regression, instead of just seeing the two variables, you're going to see one or two extra things. These R values. So these R values are a measure of how good the fit is. I said it goes from 0 to 1. This fit, it's 0.999999999. It's almost, it basically is perfect. This curve we have models the data perfectly. All right? So that's how you can get an idea of how good of a fit you have. If I, just to show you, let me change one of these points. Let me mess it up. Let's change this to 39. Now if I do that, my points aren't going to be as nice of a line, meaning that the curve that it finds isn't going to be quite as good. So the R value is going to be a little lower. It's not bad, but it's not 0.999999. Now it's about 0.997. Still an excellent fit. Okay? But if you change some other points and mess them up even more, you could get that R value to drop. Any questions on that? Calculating a power regression by hand or on the calculator? All right. Okay, so the homework tonight, it's on 293. Okay, it's 35 to 37, 39 to 41, 43 to 48, but you can skip 45, and 51, 54, and 55. And you've got a little over 15 minutes or so. So there's some extra books, okay, if you want to try to get started on it. Tomorrow we will finish up chapter 5, and that'll finish up everything we're going to do before the Thanksgiving break.